And so now we are ready to discuss how all of this applies to series of functions. So we already talked about power series, we already introduced them, but now I'm going to speak in slightly more general terms. Let's try to define a series of functions. So given a sequence of functions fn on some interval I, the series of functions will be defined in the following way. The series sum from 1, it would be from 0, from any number, to infinity of fn is a function if it exists, actually. Defined on some subset of I, as follows. Sum from 1 to infinity of fn is equal to the limit as m goes to infinity of the sum n from 1, in fact let me use k here instead of m. K goes to infinity, n from 1 to k of fn, right? So if this limit exists, then the series converges. If a limit does not exist, then the series does not converge. All the usual stuff. But again, in this case, things are more complicated because we're talking about convergence of a series of functions, right? So in this case, the partial sum, so this is a partial sum, and the partial sum is a function defined on the interval I, right? Now, so the series, the sum of a series is a limit of partial sums, same as always. But again, because we're talking about convergence of functions, we already know that there is more than one notion for convergence, right? If the limit exists pointwise, is taken pointwise, then the series converges pointwise. And if convergence, if sum from 1 to k of fn, if partial sums as k goes to infinity converge to the sum of the power series uniformly on some subset of I, then the series converges uniformly on that subset. And I'll do a few examples of this later on, so it will make more sense. The principal point is that because we have two types of convergences of functions, then depending on which type of convergence I consider, I would say that the series converges either in this sense or in that sense. So just uniformly. Okay. Then immediately we can formulate the following theorem. Suppose that the series sum from 1 to infinity of fn, right, again, fn is not a number, right, fn is a function, but I'm writing fn of x because I want to emphasize that we're working with functions as objects, not with their values, right? Uniform convergence applies to the entire function, not to individual fn of x, right? Because we're dealing with distance between functions. Distance between functions is a number, right? Okay, so suppose that this converges uniformly on I, and fn is continuous on I for all n greater or equal than 1. What's the conclusion? Then sum of the series is a continuous function on I. And the proof really lies on another theorem that we proved last week, and that was that if I have a sequence of functions that converges uniformly, sequence of continuous functions that converges uniformly on some interval, then the limit of that sequence is a continuous function. And the proof is actually a couple of lines. If fn is continuous on I for all n greater or equal than 1, then each partial sum n from 1 to k of fn, right? That's a sum of k continuous functions. This thing is a continuous function on I. Also, because the series of fn's converges uniformly on I, what does it mean? The only thing it means is that the sequence of partial sums is a sequence of functions that converges uniformly, right? So this is equivalent to saying the sequence n from 1 to k of fn converges uniformly to some limiting function, converges uniformly on I. as k goes to infinity. All right, and then by a theorem from last time, I have a sequence of partial sums is a sequence of continuous functions that converges uniformly. So therefore, by theorem, that theorem, the sum from 1 to infinity, sum of a series is a continuous function. Right, and that's it. So this proof is complete. Okay, so before we do examples, let's actually prove all the theorems, and then we'll just use them in examples. All right, so now I know that if I have a series of continuous functions that converges uniformly, then the limit must be continuous. So now I have to find some sort of a criterion which will tell me if I have a series of functions, whether or not this series converges uniformly. And again, I will not be able to do anything there directly because I don't know what the sum of a series is. So we have to resort to Cauchy sequences. And let's see what we can do here. So rather than checking that the sequence of partial sums of Fn, that the sequence converges uniformly on I as k goes to infinity. We want to show, or we can show, it might be, in fact, maybe let's rewrite it this way, it might be easier to show. The equivalent statement that the sequence of partial sums is uniformly Cauchy on I. Right, because that is an equivalent statement. And now what does it mean to show that the sequence of partial sums is uniformly Cauchy on I? So this will be true if, once again, for every epsilon greater than 0, there exists an n in R such that, so in this case, I'm going to take m and n in such a way so that m is smaller than n. So such that, right, when I'm saying n and m bigger than capital N, I can always call the smaller number by m. It really doesn't change anything. So such that n bigger or equal than m greater than capital N, that this would imply that we had two definitions. I'm going to write a supremum definition. Supremum x in I of absolute value of what? Of a difference between fn of x and fm of x. Now I'm running into some notational problems. Let me make a change here. So when I'm doing my partial sum, the index actually is a dummy number, right? I can have sum of fn, n from 1 to k, or I can have sum of fl, l is from 1 to k, right? This really doesn't change anything because it still denotes the same sum, right? If I have a sum in L from 1 to 2 of F1 plus of Fm, so let me just write this down for a moment. Sum L from 1 to 2 of FL, this is F1 plus F2. If I have sum, I don't know, Z from 1 to 2 of FZ, this is still F1 plus F2. So it doesn't really matter how I call this number, this index, right? At the end of the day, it's a dummy index which will disappear. So I'm going to replace N by L in this statement here. Right, so notice that I modified this statement. Okay, so then what I want to do, I want to take partial sum that ends at n, right? Because I want the sequence of partial sums to be uniformly Cauchy. So I take nth element of that sequence of partial sums, L from 1 to n of FL. And from it, I have to subtract the partial sum that adds up to m, L from 1 to m of FL. And this is less than epsilon. All right, and actually, again, this I can rewrite in a slightly different way. So what do I know about this difference? Here I'm adding everybody from 1 to n. Here I'm adding everybody from 1 to m. M is smaller than n, so this sum contains more terms than that sum. But in principle, there are a lot of common terms. In fact, all terms from 1 to m are common between two sums, so they will disappear. And they will cancel out, right, because I'm adding and subtracting the same thing. And so what's left is a sum L from what? From m plus 1 up to n of FL. But then by rearranging m and n, I'm going to be a little bit careless here, but we can carefully show that this actually is going to be true. Then that just means that I can, by shifting index, I can start from m. So this is equivalent to saying that the supremum as x belongs to I of the sum L starts from m and ends at n of FL, that this is less than epsilon if m and n are bigger than capital N. Okay, so this is just a criterion which tells me that my sequence of partial sums is Cauchy. And because it's an important criterion, so really it's nothing but just saying that the sequence of partial sums is Cauchy. Because it's important, it has its own name, and in fact it's a repetition of the same name that we've seen before. There was a Cauchy criterion for regular series, so now there is a uniform Cauchy criterion for a series of continuous functions. All right, so let's formulate it then. A uniform Cauchy criterion. All right, so actually let me combine two things. What did we decide? We decided that if the sequence of, actually we decided it here, if the sequence of partial sums is uniformly Cauchy, then the sequence of partial sums converges uniformly, or everything on the interval I. But the criterion for uniform Cauchiness is this statement here. So if this statement verifies for every epsilon, then that means that my series of functions is uniformly Cauchy, and therefore it uniformly converges. And so I'm combining these two statements to mean the following. If for every epsilon greater than 0, there exists a capital N and N in R, such that if N is greater or equal than M greater than capital N, that this implies that the supremum over X in I of the sum L from M to N FL of X, this is less than epsilon, then the series N from 1, or L, let's use L here, L from 1 to infinity of FL, the series converges uniformly on I. Right, so this is a statement that we need to verify to decide if a series converges uniformly on a given interval. Okay, now two additional theorems will follow from this. So theorem number 1, you'll recognize it because it again appeared before for series, so now we just produce its analog for functions. If the series n from 1 to infinity of fn converges uniformly on I, then fn converges to 0 uniformly on I. Right, this was stated as a criterion for divergence before, right, for a sequence of numbers. If the sequence, for a series of numbers, if a series converges, then the term of a series goes to 0 as n goes to infinity. So this is a similar statement, right? If the series of functions converges uniformly on some interval, then the functions that form the series must go to 0 uniformly on I. And so let's prove this. One thing actually that is true, right? Cauchy criterion implies uniform convergence of series, but uniform convergence of a series also implies a Cauchy criterion, right? Because Cauchy sequence and the convergent sequence means the same thing. So let me just add it here. Our direction is also true. Right, if a series converges uniformly, it's Cauchy. If a sequence is uniformly Cauchy, if it's uniformly Cauchy, it converges uniformly, right? We proved that. Okay, so let's copy this statement. If a series converges uniformly on I, then Fn, or series, satisfies the Cauchy criterion, the uniform Cauchy criterion. Let's add this abbreviation so that I don't write it all the time. So then let's satisfy the uniform Cauchy criterion. That is, for every epsilon greater than 0, repeating the same thing again, there is an n in R such that n greater or equal than m greater than capital N, that this implies that the absolute value of the sum L from m to n of FL, this is less than epsilon, and there is a supremum that I'm missing here. So let me do the appropriate modifications of X and then supremum. Okay, but then if that is true, in fact, if I choose n to be m equal to n, right, which I can little m equal to little n, which is going to be fitting here, then I have the supremum n equal to m. Supremum as x is an I of the sum L from n to n of FL of x. I'm going to put epsilon in front, so epsilon greater than this. But then what is the sum from n to n, right? It's just Fn. So this is supremum x in I of absolute value of Fn of x, right? But then I can always write supremum of Fn of x as supremum x in I of Fn of x minus 0. And this supremum is less than epsilon. So what I have just written is a definition of uniform convergence of the function Fn to 0. So therefore, Fn converges to 0 uniformly. On I. Right? Again, supremum of Fn minus 0 is a number which I can make arbitrarily small. So that means that uniformly my Fn, the graph of Fn, is going to be close to 0, right? Everywhere, for all values of x. And so with this, if we can check now that the supremum of the functions in your sequence, if it does not go to 0 as n goes to infinity, that means that the sequence of functions cannot converge uniformly. This will be, so it's sort of a test of the luck of uniform convergence. It will be useful later on. And the last theorem that I'm going to prove now, this is something called Weierstrass M-test. And this is simply a useful test, useful in the sense that it makes application of a uniform Cauchy criterion easier. So let's suppose that absolute value of fn of x, actually let me write it as in a slightly different way. Suppose that the supremum as x is in I of fn of x is less than some mn, right? Some real number, or plus, positive real, non-negative real number. In fact, positive because I said less. That this is true for every n, and suppose that I know that the series from 1 to infinity, that this guy converges. Right, it's kind of reminds me of the comparison test, right? So I have that my series of sequence of functions is less than another sequence of numbers, and the sequence of numbers converges. So then comparison test for numbers would have told me that that means that the series of functions converges, and in this case not just converges but converges uniformly. So then the series of fn converges uniformly on I. And the proof will require the use of Cauchy criterion again. All right, so what do we know? Because the series of mn's converges, that series of numbers is going to satisfy the standard Cauchy criterion. And what that means is the same thing as what we have written here, except that because it's a series of numbers, there is no need to take a supremum. So for every epsilon greater than 0, there is a capital N in R such that m and n, n greater or equal than m greater than n, that this would imply that the absolute value of the sum L from m to n of ml actually, that this is less than epsilon. Okay? All right, but if that is true, so what do we have now? Let's look at the similar sum, but for functions. If I take a sum L from m to n of fn of x, and I want to take absolute value of that, what should it be? That's absolute value of the sum by triangle inequality. This should be less or equal than the sum L from m to n of absolute values of fn of x, right? But also by our assumptions, what do we know? We know that the supremum of fn of x is less than mn on r plus, right? So that means that this is going to be less or equal than the sum L from m to n, right? Fn of x, absolute value, is less or equal than mn. So mn, and this in fact is true for every x and I. And what I know about the sum of mn's? Well, mn's are, let me see, again, I need to be careful with my index. The index was L. FL of x, FL of x, ML. Now, I know that ML is a positive number, right? So the absolute value sign here really is an extra that I don't need. I can drop it, right? And then I see that this sum is the same as the sum over here, so it must be less than epsilon, right? And so that means, because this is true for every x in I, so therefore the supremum x is an I of all these jars, sum L from m to n FL of x. The supremum should be, in principle, less or equal than epsilon. But then by modifying the proof a little bit, I can actually make it less than epsilon. In fact, let's do that right now. So let's see. How do I modify my proof so that I can put less than epsilon here instead of less or equal than epsilon? Well, I can do the same thing as I did with the proof a little earlier today. Let's actually make the mn business less than epsilon over 2, right? So then that means that this is going to be less than epsilon over 2, which means that the supremum is less or equal than epsilon over 2. But if it's less or equal than epsilon over 2, it's automatically less than epsilon, right? And so that is going to be true as long as n is greater or equal than m greater than capital N. Well, but what does it mean? It means that I proved the Cauchy criterion, right? That for every epsilon greater than 0, there exists a capital N, such that if n is bigger than m, bigger than capital N, then this quantity is less than epsilon. So therefore, uniform Cauchy criterion is satisfied, and therefore my series converges uniformly. Uniformly on I, right? All right, so this establishes all theoretical foundation that we will need, and so in the next lecture I'm going to do a bunch of examples that will utilize all the machinery that we developed so far.